What's up everybody, I'm David Wilson and welcome to the Dev Aspect. In this episode, we're going to continue building on the data model and game logic we've been building in the previous two episodes and put that together with the actor model. This will allow us to create a game engine that can process updates to the game world state concurrently while other things are happening in the application. The actor model is a computational model that's built upon message passing between different components in the application's architecture. This message passing allows the actors to communicate both information and actions between the different components in the system. This is interesting in functional languages because each actor contains its own state which is not shared between the other actors. This removes a lot of the problems of shared mutable state between different components in a large application. Some implementations of the actor model allow the actors to be either in different processes or different machines. This allows the application architecture to be much more resilient because there's no single point of failure. And if this is starting to sound like microservices to you, then it's not very far from the truth. These models share a lot of similarities, so a lot of the same ideas apply. And the actor model is not actually constrained just to functional programming languages. In .NET, there is both Akka.NET and the Microsoft Orlean framework, both of which providing their own implementation of the actor model. For the purpose of our game code in this episode, we're going to use F#'s MailboxProcessor. The MailboxProcessor gives us a simple implementation of the actor model that lives within the same process and may or may not use multiple threads. It also allows us to use an immutable object to manage state, so we can still leverage a lot of the cool things that we've learned about functional programming so far. So to show you how the actor model is cool, let's jump into the game code and I'll develop the main event loop for our game engine. So let's get started by using the data model and game logic code that we wrote in the previous two episodes. If you want to follow along, you can download the code from a repository on GitHub at github.com/thedevaspect/aspect-f#. I'll leave a link to that in the video description below in case you want to get there easily. One thing that a viewer pointed out to me from the code in the previous episode is that I was not using the most efficient way to get the exit information for a particular direction. So if we take a look at our direction functions, you can see that we were using a parameter destructuring before to pull the north exit information out of the record that's being passed in for exits. As Milo Cooper pointed out, it's much easier to just pass in exits and then grab the direction information directly off of that record. And he's totally right about that. It's way simpler this way. The main reason for showing the destructuring syntax is just to show how function parameters can be pulled apart in interesting and useful ways. But in this case, it makes sense to just go ahead and do it the simple way. So we're going to go ahead and change the code to what Milo had suggested. Okay. So in the code that you download from GitHub, you won't need to make these changes. I'll have already committed those changes in the initial state of the code. So let's go ahead and start looking at the MailboxProcessor class. The goal we have today is to create a game engine that's capable of maintaining the current state of the world and then process any updates to that state that come in based on the actions that the player performs. So it's really easy to get started writing a MailboxProcessor, so we'll go ahead and start that now. So we'll call MailboxProcessor.start. And this method is what will start our mailbox processor and create the necessary context for its message loop. The parameter to this method is a function that takes the message queue as a parameter and then encapsulates the logic for taking messages off of that message queue and then acting on them. So we'll write fun inbox, which gives us a lambda function with an arrow. And now we need a loop that can read messages off the queue and then do something with them. To do this, we'll create a recursive function that will continue to call itself every time it handles a message and then starts to receive another. So let's call that letRec. And rec is the symbol you need to use, or the keyword you need to use whenever you want to define a recursive function. Inner loop, world state. And basically what this means is we're defining a recursive function that takes the world state at any given time and then processes any messages that come into this mailbox processor, which might have some effect on that world state. And then inside of that, we'll create a computation expression. And this is a feature of F# that allows you to write simple code that actually executes asynchronously. If you've used the async await keywords in C#, then this is sort of similar to that. The idea is to write code that looks synchronous while it actually runs asynchronously and concurrently with other code that may be running at the same time.
We'll go into more detail about computation expressions in a future episode. So now we'll take a message off of the message queue. Inbox.receive. So receive is the method that will dequeue a message from the message queue. And you can see that it has an optional timeout. So if you are in a case where you actually want to have a timeout for listening for messages because you don't want to wait forever, then you could put a timeout there. But for now, we're just going to leave it without a timeout because we want to wait until another message comes in. So now we pulled a message off the queue, but we don't really know what type of message we're dealing with yet. So now let's go define a message type. And we'll use a good old discriminated union for this purpose. So we'll call it game event. And we'll start with a union case called update state. And to process an update to the game world state, we need to send a function in that will actually do the transformation to the world state. So let's use a function type signature here. So we want to take in a world, and then we want to use our result type from the previous episode to specify the success and failure information for this transformation. And we're going to use a string as the output because we're just using strings for failure information. So the only other thing that we need right now is a case to tell the loop to exit. So let's have another one called end game loop. So now that we have our event type, we can go back and use a match expression to deal with the message that comes in. So we can match event message with update state and its corresponding update func, and also end game loop. So in the case of update state, we want to be able to apply the update function to the current world state and then return it, or at least pass it through to the recursive function so that it gets used for the next message that gets received. So this is what lets us emulate the use of mutable state while still using immutable data structures. So we'll say return, and then we'll call this inner loop function recursively and pass it the result of calling the update func on world state. But the problem we have at this point is that update func returns a result and not a new world state. So we need to pull that world out of the result so that it gets passed back into the inner loop function on the next recursive call. So for that, we'll create a new function that will do the update for us and then return the world object depending on whether the update succeeded or failed. So let's call that function apply update. And it will take in update func and the current world state. And in this case, we just need to do a match expression to process the result of calling update func on world state. So for success, we're going to have the new world state. And for failure, we'll have a message that we need to deal with. So obviously in the success case, we can just return the new state of the world. And for failure, we need to write out the message and then return the previous world state because the update operation was not successful. So we don't want to change anything about the world state. So let's use printfn and use a couple of new lines just to give it some space. And then print out the message. Then return the world state. And one more thing we want to do here is, in this case, whenever we actually have a successful update, we kind of want to see what the new state of the world is at that moment. So we should print out the state of the world after the transformation occurs. Luckily, in the previous episode, we made some functions that are capable of printing out the current world state, so let's use those now. Describe current room with the new state of the world. Then we'll pipe that through to display result. And now I think our function is pretty good. We have the ability to update the world state using the update func and then do something based on whether that operation succeeded or failed. So let's go back down here now and then use apply update. And because apply update takes the update func in the world state, then we really don't need to change much here. So for in game loop, what we need to do is stop calling the recursive function so that it doesn't continue reading messages off the message queue. So in this case, we're just going to return a value of type unit, because ultimately the recursive function and the mailbox processor aren't returning any values. They're just doing some computation. And the last thing we need to do to make this mailbox processor work is inside of our function, we need to invoke the recursive function for the first time. So we'll call inner loop, and we'll give it the game world, which is our previously defined game world state. And now we're looking pretty good. It looks done. So let's run all this code and see what happens. Okay, it looks like the run succeeded. So now let's try to send a message to our mailbox processor. So we'll call the post method. And you can see there are a few different post methods. And what these methods do is they send a message to the message queue of the mailbox processor, and they put it in the right thread context depending on whether the mailbox processor is running on a different thread. So all that stuff is taken care of. You can see that there are a few different post methods. One that just basically posts a message and then keeps moving forward. Another that posts and waits for a reply asynchronously. Another that posts a message and waits for a reply synchronously, etc. So the idea is that various actors that are running in the application should be able to use these methods to send messages and receive replies from the various actors and mailbox processors so that they can synchronize their behavior. But in this case, all we really want to do is just send a message to the game loop so that it processes an update to the world state. So the simplest thing we can do is just send the in-game loop message. So if I send that by hitting Alt/, then it basically returns unit, because that's actually the result of our inner loop function. Whenever you exit, it returns unit. So that worked. Now let's start up the game loop again by running this code with Alt-Enter. And now we can send an update state message. And since what we need here is an update function, we can actually just send our move function that we wrote in the previous episode. So now let's send move south. I hit Alt/, and it shows that we are in a cold room, which is south of the starting room that we've defined in the original game world state. So the whole point is that after any update function that gets run on the world state, we should be storing that new world state so that any future messages get processed against the new state of the world. So if we try to move north, it should send us back to the center room. So now we ran that, and we're back in a central room. So it seems that we've maintained our world state. Also, if we try to make a move that is not valid, like if we move east, then we'll still get the failure information written out as we expect. So it says that there's a locked door in that direction. And now if we try to move south, then we should be back in the cold room again. And there we are in the cold room. So depending on whether the update function succeeds or fails, the world state will either be updated and then passed along to the next recursive call, or if it failed, then we'll return the current world state without any changes. So this is pretty nice. It allows us to have this message loop going where we have some simple code that's just pulling messages out of a queue and acting on them, while our application code is free to continue doing other things while sending messages to the game loop to cause things to happen in the game world. One thing we might want to do is put a better interface on this mailbox processor so that other components don't need to know how to send messages to it. They just call methods using a more specific API that is tailored to the semantics of the game loop. So we can define a class that wraps this mailbox processor. So we can say type GameEngine equals, and then we'll just go ahead and indent all this code because we're still going to take this game loop and keep it as a private variable inside of the class. And we can just call this game loop now. Now we can define member methods that will take care of sending the messages into the mailbox processor's queue. So if we type member this.apply update, then pass in an update func, then we can send the message to the game loop. We'll post it and send update state with the update func. And similarly for the in-game loop message, we can have a member function called this.stop, and it won't take any parameters, and it will just send the in-game loop message. So now we have a more clear interface for interacting with our mailbox processor. So now we can go ahead and evaluate this code. and then create a new instance of our game engine. Then evaluate that. And then we can basically do the same thing that we did before. GameEngine.applyUpdate. And then we can send move south. When we run that, we see that we're in a cold room again. So now we have a really clear interface where we have an apply update method that makes it obvious how to interact with this mailbox processor. One more thing that we might want to do is make it so that we can pass in the initial world state to the game engine when we construct it, so that we're not using some predefined game world state. We can pass in any initial game world state. So it's really easy. Let's just go ahead and pass in an initial state here as a constructor parameter to this class. We'll call it initial state, and specify that it's of type world. And then here, when we have the initial call to the inner loop recursive function, we can just give it the initial state. So now we can reevaluate this code. And we also need to pass in game world here so that we have the initial state passed in. And then we can apply the update to move south. And once again, we have the same result. So at this point, you're looking at this and probably thinking, well, this looks pretty similar to just calling a method on a class that has its own mutable state. How can this really be concurrent? Well, let's prove this code is running concurrently by creating another mailbox processor that will cause the player to wander around aimlessly in the game world. So let's create a new mailbox processor called player controller. And for this one, we're going to use a timeout so that after waiting for some brief amount of time for a message to come in, the player controller will take some action, which in this case would be picking a random direction to move to. We'll set a timeout of 2 seconds by specifying 2000 milliseconds. And the way that timeouts work is that the receive method will throw a system.timeout exception. So now we'll get to see what a try catch looks like in F#. We'll have this with a with keyword that looks similar to a match expression. And for one of our cases, we'll have the type comparison operator, which will be looking for system.timeout exception, and use the same arrow syntax to denote how we want to deal with this timeout exception. So here what we want to do is define a list of directions that we might want to go, and then randomly pick one of them, and then use that as our update function to send an update to the game engine. So we can define a list that contains some tuples that say what our directions are, our possible directions are. So we'll say north with the direction function of north, south, east, and west. And since we have commas between these two values, this is defining a tuple, and each line is an individual item or value in the list. So this is a list of 4 tuples that have 2 parts. Now, we want to pick one of these tuples randomly. So what we can do is pipe this through the list.item function. And list.item is expecting an index to pick an item from the list. So since we're in .NET, we can use system.random to generate a random integer between 0 and 3, since we have 4 items in the list. So we should go ahead and create one of those. Now we can use it to call ran.next with a parameter of 4 to say that we want to pick a value between 0 and 3. And you'll notice that we use the parentheses on the outside of the method invocation. And that's because method invocations in F# don't need the common parentheses and comma syntax as you would normally see in C#. So what we're doing here is we're invoking this method inside of the context of calling list.item. So now we should have a randomly selected direction from this list. So let's do something with that. So now we'll create a lambda function to destructure the tuple that's selected from this list and give it the parameters direction and direction func. And what we want to do now is print out the direction where the player is wandering. And we also want to return the direction function so that we can pass it on through the pipeline. So for that, we'll use the semicolon, which allows us to put an additional expression into this function. And its value is what will be returned by this function. So we can put direction func here. And since we're piping this function through, we can actually just pass that directly into move and create a partial function application of move with the direction function piped into it. So now that we have that move function, we can pipe that directly into GameEngine.applyUpdate. So now we've got this logic that allows us to randomly pick a direction and build the move function and then eventually pass that directly into applyUpdate. So we're not totally finished yet. We still need to define the message type for the player controller. And in this case, we're just going to take a string because we only have one message that we want to give the player controller, which is to stop wandering around. So let's go ahead and just say if event message equals stop, then return a unit value. So now we have our entire mailbox processor for the player controller. And lastly, we just need to do the first invocation of the inner loop recursive function. And since we don't actually care about the state, we're just going to give it 0 and then let that just get passed into every recursive function call. Oh, which reminds me, we're missing something here. So in the case where we handle the timeout exception, we actually need to call the inner loop function recursively so that we continue the loop after handling the timeout exception. So let's go ahead and, so for that we'll write do inner loop and state. Because we don't care what the state is, we're just going to call the recursive function again. So now this is all done. So we can go ahead and try to evaluate this again and see if our player controller will start wandering around randomly. So after 2 seconds, the player started wandering west. And you can see that there's no room in that direction. So the player will pick some incorrect directions at times, and then it will pick some that do work, like moving north. So we can see we're in the cozy room. So both of these mailbox processors are operating concurrently. And that doesn't necessarily mean they're operating on different threads, but they are operating sort of independently. They have their own message loop that is receiving messages and processing them based on its own current state. So now we'll go ahead and just stop the player controller so he stops wandering. And we'll send the stop message. And now the player controller stopped. And I want to point out one last thing that's interesting about this. Because we're using immutable data structures, and because our mailbox processors are built using recursive functions that are passing the world state object through after receiving each message, we can actually send in an entirely new world state at any time that we want so that we can reset the world state if we want to start over, or for testing purposes or anything like that. We'll quickly add a new case to our game event. We'll call that reset state, and we'll take a world record instance. And in our match expression, we can accept this reset state and then just take in the new state and then do the same recursive call with a new state. So anytime reset state gets received, it's basically just going to continue calling the recursive function with this new state. We can also add a new member to easily reset the state. And we can reevaluate all this code to start up our mailbox processors again. So now we can see that our player is wandering. And at any time, I can call GameEngine.resetState, and pass in the initial game world state. And then I can run it. And now he's moved north and he's back in the dark room. So at any time, while the player is moving through the world, I can reset that game world state because we're using immutable data structures and we're not tied to a particular mutable instance of the game world state. So it makes it really easy to test your game while it's running. So as you can see, F# actor model made it really easy for us to create two actors that are operating concurrently within our game application. It allowed the player controller to communicate with a game engine to make changes to the game world without relying on shared state. Keep an eye out for the next episode because we're going to implement a command parser that will allow the player to use text commands to start to interact with the game world. If you're looking forward to that and want to know when the next episode gets released, click the red subscribe button below and make sure to click the checkbox to be notified of all future uploads. So that's it for this episode of the Dev Aspect. Thanks a lot for watching, and we'll see you next time.